Good morning, everyone. I am sure everybody was enjoying that music and maybe doing a little happy dance for Friday. We'd like to welcome you today to the Traffic 21, Mobility 21 Transportation Center Deployment Partner Consortium Symposiums Research and Education Showcase. My name is Lisa K. Schweier, and I am the Program Manager for Traffic 21 and Mobility 21. Also on the call with us today is the Director of Traffic 21, Chris Hendrickson, the Executive Director of Traffic 21 and Mobility 21, Stan Caldwell, and our Senior Administrative Coordinator, who has really been extremely valuable in getting all of the things coordinated for today, Joy Mann. So thank you all for being here today. And thanks to everybody else who has come back. We had our first day of the symposium yesterday, and we have had the pleasure of hearing from national experts on equity and mobility, as well as the impacts of COVID-19 on mobility. And we're excited today to continue the conversation by hearing from our researchers and students about the research and education that's happening on the campuses. This Deployment Partner Consortium is engaged for identifying real-world transportation needs, research project development and deployment, technology licensing and commercialization, student recruitment for jobs and internships, class and capstone projects. Putting our research, development and deployment approach into action, this annual symposium provides an opportunity for interaction and discussion among researchers, students, and deployment partners. And we're excited to have such an interactive way to be able to have those discussions with you. Please note, this session is being recorded and all participants' microphones are muted. We will have an opportunity after the presentations to ask questions and engage in discussions by joining a breakout room or maybe by having a question and answer session. You can also add comments to a virtual idea board, and I will be posting in the chat box the information on that board. So now I would like to introduce this session's speakers and the topics they will be discussing with us. First, John Peha, who is going to be talking about spectrum policy for connected vehicles. And his student, Jeremy Pessner, is also going to be part of this session. Robert Tamburo is going to be talking about real-time obstacle detection and traffic analysis. Ding Zhao and Peide Huang is going to be talking about development of a safe, profitable, and fair Robotaxi strategy. And Venkat, Viswanathan, and Matt Guttenberg will be talking about INCEPTS, software for determining optical placement of electric vehicle chargers. So we're going to start first with John, and I will stop my screen share. And John, if you would like to begin.
Okay, thank you. Give me a second to get my screen shared. There we go. So hi, I'm John Peha. I'm going to talk about spectrum policies for connected vehicles. The bad news for you is that it's me and not Jeremy Pessner, because my students are all better at this than I am, but that's the way it goes. So first of all, what on earth am I talking about? Connected vehicles are wireless communication systems for vehicles that includes vehicle-to-vehicle communication, vehicle to roadside infrastructure that's nearby, and vehicles to these and everything else, which is basically what V to X. And I'm going to be using that V2X acronym throughout this talk. Oh, I can turn my video camera on. And the spectrum policies for V2X systems have been very unclear, in part because the Federal Communications Commission and the Department of Transportation, the two primary federal agencies for making decisions on this issue, have been very much in disagreement. Actually, to make the slides that have been posted already slightly outdated, 2 days ago, the FCC voted to make some significant changes, but you'd think that might bring clarity, but of course we have a new administration coming in January. So there's still plenty of lack of clarity on this issue. You can trust that regardless of where this goes, CMU researchers are going to be looking at the implications for everyone involved. In general, we are doing research on both the spectrum and the infrastructure issues of V2X. In particular, in this talk, I want to talk about whether spectrum should be shared between V2X and other kinds of systems like Wi-Fi, or whether it should be exclusive to V2X. But we're looking at lots of other issues, including how much spectrum should be allocated, which frequencies, with infrastructure provided by whom, using which technology, centralized or decentralized. There are a lot more issues here to look at. This is one. And so in particular, I want to say, imagine that we divide up V2X traffic in two categories and separate them. There is traffic that is safety critical, communications traffic that is safety critical and latency sensitive, things like crash avoidance. And then there's a lot of other traffic, which may be quite important, but is either not specifically safety critical, it doesn't involve crash prevention, or is not latency sensitive. And I want to imagine that that latter category is shared with these unlicensed devices or not. The question is that a good idea? And in 7 minutes, I can only show you one slide, so this is my favorite. In one particular scenario, I want to say how much, would you need more spectrum to provide lots of throughput for these systems if you shared and if you didn't? So the x-axis here shows the throughput of V2X traffic. The color actually is meant to show the throughput of unlicensed devices, in particular Wi-Fi. I'm sorry, I should have said the scenario better. DSRC technology, basically 2,000 people per square kilometer, sort of a medium-sized city. All the cars have these devices. This is just one scenario. We're looking at lots of scenarios. And the y-axis here is how much spectrum would you need to achieve this throughput? And the bottom curve says this is how much spectrum you would need if you allow these things to share with each other. And the top curve shows how much you would need if you gave V2X its own band and unlicensed devices their own band, which ironically is what both agencies have been calling for of late, but have not always. And you see we can cut the amount of spectrum you need by basically a factor of 2, which is quite a lot. So what I conclude from this is that sharing between the non-safety critical traffic and other kinds of devices is really quite efficient. There is some degradation, but the benefits of sharing outweigh the damage that these things do to each other, especially if it's indoor Wi-Fi. But even when it's outdoor Wi-Fi, which is a little bit more problematic. That we should look at doing this. And we should consider not only allowing unlicensed devices into the ITS band, which we have done before, but allowing V2X into the unlicensed band. And this is even more important given what the FCC did this week, because now there's less ITS spectrum based on this week's decision. I'll say one more thing, which has changed a little bit this week, but I've also been saying that we need to fix the process. We can't have agencies trying to make decisions this way, and have proposed an interagency task force as a better way to do that. Involving all the federal agencies, involving state and local government, involving telecom and auto industry. And that may change a little bit after this week, but I still think it is important that we change this process going forward. And there's more information in those papers, and I'll stop there.
John, thank you so much for your presentation. If you can stop sharing your screen, we're going to hold on to questions till we move into breakout rooms. So please keep a note of them, or you can also park them in our idea board, which I had put up in the chat. So thank you for that, and we will be back to you for sure. And next, I'd like to introduce Robert Tamburo, who is going to be telling us about real-time obstacle detection and traffic analysis, or sorry, analytics. Can you please share your screen, Robert?
Yeah, I will do that right now. Good. Okay, thank you.
Yes,
so my
good,
name.
Thank you.
Okay, thanks, Lisa K. So my name is Robert Tamburo. Today I'm going to very quickly talk about two projects that we've been working on to address mobility issues. The first is a device, a sensor that we built called a light curtain. And this device allows us to detect only objects that intersect the light curtain. So the way it works is that we project a light plane into the scene as well as an imaging plane. Where those two planes intersect at a specific depth, shown here at the rabbit, where the two planes intersect the object is where we detect an object. So you can see in the upper right, the camera image is the return to this camera sensor. So we see this little slice out of the rabbit. Not too useful until you scan both of the planes throughout the scene, and then you could scan the rabbit completely and get an idea that there's an object in this at this depth. So for demonstration purposes, this is happening really slow, but in practice, it happens at many hertz faster than the eye can see. So the image would actually show the rabbit. So we built the device. This is what it looks like. So again, we can detect objects that pass through the curtain only. We can actually program the curtain to take on many different types of shapes. So this gives us great flexibility for different types of applications. The range of it currently is 15 meters, and that can be extended by increasing the power of the light sheet projector. More importantly, it has a 50 hertz update rate, so we get an image 50 times per second, which makes it suitable for automotive applications, for example. And I'll show you some examples of that. So we strapped this device to a vehicle and we drove around the city to capture some data. What you're seeing on the left in blue is the actual light curtain shape. So it's a plane in front of the vehicle as well as two planes on the side of the road. And we kind of use this as like a quote unquote lane monitoring device. So any object that passes through the blue area, our light curtain, is an object that we should be aware of. And that is shown as green. And on the right is our light curtain shown in blue again with the colored detected objects, but we also show the results of LiDAR data, which is shown in white. So you can see LiDAR is very sparse. It captures, returns of many objects in the scene. So like visual cameras, you have to parse all of this data to figure out what's going on in the image, detect objects. But our sensor has the advantage of being high resolution, real time, and requiring very little processing. So here's another example of our light curtain where we changed the curtain to just be a plane, but we're scanning at different depths, and we're able to detect, vehicles, people on bicyclists, for example. So the idea here again is to have this flexible platform or sensor, I should say, that can very easily detect objects that pass through it. So I'm going to switch gears. Well, let me state first that, so we're demonstrating this on a vehicle. So this can be used for, robots, for navigating robots, for navigating cars. It can also be used as a simple sensor for like counting people or counting vehicles, for example. So if you think of installing this sensor at an intersection, you can count the number of people that pass through the intersection. Which leads me to the next project where we wanted to understand using cameras and computer vision algorithm development, complex activity at intersections. We're interested in intersections because they are points of planned conflict. So this is conflict between people and vehicles. They tend to cause intersections are, tend to cause a lot of traffic and reduce mobility. They also are, pretty unsafe. So we kind of categorize the type of activities that we're interested in into two categories. Shown in orange are things that we call low-level analytics. These are things that basically are counting. So how many vehicles, how many people on bikes, how many people are waiting at the bus stop. But we wanted to learn more about the activity that happens at intersections. We call this high-level analytics, that's shown in blue. These help us answer questions more like that get to like the behavior of objects. So one thing could be anomalies that we're really interested in. So accidents are dangerous because crashes occur. Crashes are only reported sometimes to the police, so the data is kind of not complete. But more importantly, you can have a dangerous intersection where there are not accidents, but there are near collisions. So that's just an example of something that we're interested with these high-level analytics. So the goal was to develop this computer vision platform where we capture and process video data in order to like extract rich information. So shown in the block diagram is kind of two paths for a platform. On the top, the idea is that the computer and the sensor are at the intersection where so that we can do real-time analytics. John just talked about connected vehicles. So you imagine, the infrastructure sending our information to connected vehicles so that they can use it, for example, to path plan and avoid accidents. The other pathway is near real-time analytics, where we're kind of aggregating the information for people to digest later so that we can share it on a website or through apps. So very quickly, we've deployed this at a couple intersections around CMU. Generally, it consists of a camera, at least one camera, usually 4 or more. And we have a cabinet with computing equipment. In this example, we have 4 computers and 4 separate GPUs. So this just gives an example of 2 of the intersections that we have cameras installed in. Just gives you an idea of what the field of view is for the cameras. So we've developed this computer vision architecture pipeline that detects objects, tracks them, and reconstructs them in 3D. So there's some references there for anyone interested. Here's an example where we aggregate the 3D trajectories of vehicles that pass through an intersection over time. And this gives us an idea of average activity or normal activity. We also we have an idea of normal speed profiles as well. So we take that, we run our method in real time and compare it to this map to identify anomalies. So any trajectories that deviate from this is an anomaly. What I'm showing here is automatic tagging of anomalous activity. In the lower right, you see a speed profile. So you can see the green line kind of dips very quickly. Our system said, hey, there's a problem here, and we noticed that there was a near collision. In the same way, this video snippet was flagged because this vehicle with the red trajectory made a left when they weren't supposed to. So this automatically was flagged. So then the pandemic happened, and we said, can we adapt our method to learn more information about activity during the pandemic? So we had some longitudinal data, and of course we showed that, in middle of March, end of March, activity in this parking lot dramatically reduced when non-essential businesses were ordered to close. Here we were able to train a model to detect people, and then we were able to estimate the distance between people to determine if they were social distancing. Here we very quickly developed an algorithm to determine whether people are wearing face masks. So that's all I have. Thank you for your time. So those were a few projects where we are using computer vision, and we developed a sensor to improve mobility and hopefully give rich information to city planners, for example.
Robert, thank you so much. I appreciate you giving that overview, and the graphics were pretty incredible too. So thank you for including those. If you can stop sharing your screen, and Peide, if you can start sharing your screen, because you're going to be up next to talk about the project that you work on with Zhao on development of a safe, profitable, and fair robotaxi deployment strategy. Peide?
Thank you, Lisa. Can you see the screen? Nice.
Yeah.
Thank you. A very good morning. My name is Peide. You can call me Peter. I'm a PhD student at Safe AI Lab of Carnegie Mellon University, Department of Mechanical Engineering. It is my pleasure to present our ongoing project, development of a safe, profitable, and fair robotaxi deployment strategy. Feel free to interrupt me at any time if you have questions, or we can chat later in the Q&A session. Our project aims to develop a safe, profitable, and fair deployment strategy for robotaxi by studying the possibility to deploy a fleet of autonomous vehicles with different functionalities. By functionalities, we mean, for example, different sensing, reasoning, and driving capabilities. Currently, more than half of the cost of the autonomous vehicle are used to purchase sensing components. By dedicating vehicles to driving zones that require different levels of capabilities, we can substantially reduce the total cost of deployment cost. Therefore, our first step is to obtain an autonomous vehicle interaction risk heat map. More specifically, we define the risk level as the number of different interaction patterns in the specific region of interest. After synthesizing this heat map with other temporal spatial requirements, we can design a strategy that minimizes the cost by demanding autonomous vehicles with different functionality to appropriate routes while maintaining a certain level of safety standard. Our general framework is that as shown here. Today, we will focus on how to generate a heat map for Pittsburgh. So it's the blue rectangle there. We first use the Algoverse data set, which contains data recorded by one LiDAR and multiple cameras on the vehicle. The data set has information about the position and the velocity of the vehicles, bicycles, and the pedestrians, as well as map information, including the lane, center line, and the drivable areas. Learning the number of scenarios in a region is difficult for several reasons. First, it is hard to predefine the scenarios or interaction patterns, since it is almost impossible to exhaustively define all possibilities by human beings. Second, the number of vehicles are changing all the time within the area of interest. In order to address these two issues, we propose to use a non-parametric method, Dirichlet process, to handle the unknown number of scenarios, a probably infinite number of possible scenarios. We then use the Gaussian process to model the velocity field in order to handle various number of vehicles. The Dirichlet process and Gaussian process constitute the center of our method. Long story short, DPGP, Dirichlet process, Gaussian process, is a probabilistic distribution over distributions. The number of scenarios is the number of clusters of Gaussian processes. This is the heat map we obtained for the city of Pittsburgh. The darker the color, the higher the risk, or the more complex the interaction is. One trend that can be easily spotted from this map is that the intersections almost always have a higher risk level than normal straight roads, which is quite reasonable. Our ongoing task is to synthesize this map with other information about demands and traffic infrastructure to design a deployment strategy to minimize the deployment cost while maintaining safety and fairness. We plan to use a mixed integer optimization scheme. This is basically what I want to talk about today. Hope to hear from you later in the Q&A session. Thank you.
Thank you so much, Peter. I appreciate you putting together that presentation and updating us on the work that you've been doing. Next up, we will have Matt Guttenberg, talking about the project he works on with Venkat Viswanathan called INCEPTS, Software for Determining Optimal Placement of Electric Vehicle Chargers. Matt, please go ahead and share your screen.
Okay, is that good?
Yep, we can see you and hear you. Thank you.
All right, well, thank you everyone. I'm gonna talk about the software that I've been working on with Venkat. I was also Shashank for the past couple of years of my PhD. And the goal of the software is to address where we want to place charging stations for the upcoming electric vehicle fleet. Not only just for terrestrial vehicles, but also for aerial vehicles such as eVTOLs. So I want to start off by kind of stating the obvious, which is the electric vehicle sales are on the rise and they continue to increase year on year. And we want to know, where is it that we have to start to place these chargers? And so one might ask, well, where are chargers currently placed? And do we even have enough as it is to address the fleet? So in this study, they actually look at the vehicle fleet in 2025, which is estimated to be about 3 million vehicles, according to their calculations. And they looked at 100 different hotspots throughout the US and found that in 88 of these 100 locations, the charging infrastructure is not even close to what is needed. And as I mentioned earlier, this infrastructure needs to be placed not just for electric vehicles, but also for electric eVTOLs, which, you know, those air taxis that have been hyped up, and also for the small mobility such as bicycles or skateboards and scooters that you might be seeing in the micromobility area. And this is not a new problem. There are very different approaches out there for how to look at where you need to place chargers, but a lot of them look at the battery as a black box. So often they make the assumption that the battery itself is a static range or discharge, and this leads to an assumption that the battery will only operate under one scenario, which is not the ideal scenario that we want to be simulating this stuff. And it can lead to a lot of consequences, such as underestimating or even overestimating the range of these vehicles. And the latter is the important case that we want to address, because you can have a scenario such as the one on the right, where you plan this trip, you have a one-stop charging station, you start driving, and unfortunately, you don't actually make it to that charger. And that would be the worst case scenario, because now you have a car that's stranded before it can actually get to a place to charge. And there are current solutions that are out there, such as this one by Electrify America. And they're essentially looking at almost like a gridded approach to placing chargers. And they've recently completed a couple of different approaches through the West Coast, from West Coast of the United States to East Coast. But these are very expensive, especially when you do a grid approach, where these are about 70 miles apart. And when you just put these chargers in a gridded fashion, often you're going to see some that are just not as utilized as others. And that could lead to a bunch of problems with the charger itself, and maybe you're just overplacing when you really don't need to. And it's just unnecessary cost. So the way that we want to look at it in our software is we want to build it from the single vehicle up. So we start with the individual vehicle itself and put in realistic routing. So this is the same kind of routing they use in robotic simulations and stuff like that. And we use maps of the target area. And these maps are taken from various different sources. Could be shapefiles, could be OpenStreetMaps, stuff like that. And on top of that, we put in these couple vehicle dynamics and battery dynamics models. And the latter is the more important part, because we're actually letting the battery be a dynamic system that's affected by temperature and other environmental impacts. And as I just mentioned, you want to incorporate these environmental impacts. This allows it to expand the impact of the battery and also the other models. From there, we build it to a scalable model, allow the vehicles to go through and do thousands of iterations, get statistics, and then we can also do charger optimization on top of that. So that's kind of illustrated in this image right here, where we have bias spawning due to populations, and we have the vehicle specific information, the map, and it goes through this optimization loop. And real quickly, I just want to highlight that we also want to make sure that we're using high performance computing. So this allows us to simulate thousands of vehicles at once. There are some assumptions we have to do here, such as allowing traffic conditions to kind of be a constant, but this allows us to focus in on the worst case scenario and use that to fully parallelize our simulation, get as many vehicles simulated at once, and get this a really efficient and streamlined simulation, so that way we can get a lot of statistics on where we should really be placing these chargers. And so one example that I will walk through that we've recently simulated is through Massachusetts. So if we look at this particular route, we go from the eastern end to the western end. And we start out with the base case. This is like your manufacturer's data, and this is what the power is. And you start adding in these calculations, and you figure out that the quote unquote equivalent to the mile per gallon calculation is this energy per mile. And you see that's about 450. You start adding in these environmental impacts, however, you see that gradually the energy is going up until you have all of them included, and you can see that it's vastly higher than the original estimate. And this is why it's important to include this kind of information. And then so you can kind of look at the differences in that one route from traveling east to west versus west to east. And you can see there's a very large gap in where you start in one and where it ends up. So we can see that there's almost a difference of 20 miles just due to where the environment is impacting the vehicle. You can do it for a different type of vehicle, which is a Tesla Model 3, get similar kind of results. And then when you look at the fleet analysis, you see that by the time you get towards the 200-mile range, is all the way out by 16,000 seconds, there's about a 25% difference in saved charge just due to these environmental impacts. You can look further, see the distance, and this is something that you won't see from other analysis because you get two different energy peaks just based on where the vehicle's heading and whether it's with the wind, against the wind, with the slope, against the slope, stuff like that. And then you can look at it. This is now looking at Delhi where we actually look at it. So these larger dots show higher utilization of chargers in these locations. And then you can even go further and look at different climate impacts and say, well, some of these locations see more utilization during cold weather, some of them see more utilization during hot weather. And then you have to, from a city planner's perspective, look at this information and be like, okay, well, we kind of have to pick the middle ground. And this is why we incorporate all this information, because it lets you get this high level information. And so, you know, from INCEPTS, we can do these high level vehicles simulations, scale to large fleets, incorporate all this information for infrastructure, and we can adapt it for any place in the world, any electric vehicle, stuff like that. And we want to combine all these different open source software and data, and obviously utilize the high performance computing. So that was kind of a lot of information, but thank you. I want to thank my group, and yes, I look forward to any questions that we have later.
Matt, that was a lot of information, and I'm so glad because it's going to give us a great opportunity when we break out to have further discussions. So thank you for just kind of giving us the framework, and we will definitely be talking more. So next up is Rahul Mandaram from the University of Pennsylvania, and he's going to be talking to us about autonomous logistics services. Rahul?
Hi, everyone. It's a great pleasure to be here. Let me just set up. 1 second. All right. So let me know if you see my screen here.
We do see your screen. I don't know. There you go. Perfect.
Okay, all right. So I wanted to present just two very quick concepts, right? This is just us looking forward. One is where, we have been focused to a large extent on, making the vehicle or making, the actual truck or the mobile platform smarter by adding, more ADAS functionality and getting to autonomy with a lot of our research. And so I wanted to take a little different view as to looking at autonomous, logistics services, where we work with the existing platforms such as the trucks, but we really provide, infrastructure-based, intelligence and sensing. So this is really putting, perception machines within warehouses, at the docks, around the distribution centers, in terms of, how the actual freight and trucking systems can work together. So there are a lot of startups that look at, driving autonomously within, some kind of fenced cargo or a distribution center area. But here, this is focused much more on how can we put these sensors in the fixed environment and then do automatic teleoperation of a subset of these vehicles, where the vehicles per se, we're not going to be investing a lot or putting a lot of, software or intelligence within them. So I'm going to take give a pitch. So I'm just treating this as a mock pitch, for valet parking, which is not our logistics, end goal, but you will see that, this is a simplified version with, less of the clutter of what a logistics facility would require. So this is it's just a conceptual idea of, how we are trying to put this over here, right? So obviously we know parking is, the moment you buy a car, you also buy a parking problem with it, right? And there are a lot of hours wasted, especially if you live in a big city like in NYC. Over 107 hours per year are wasted by drivers, looking for parking. And parking garages per se, they're much more they're much more expensive than street parking. And then the next level up is, valet parking. And valet parking is really something that, most people would use on a special event, and where they're really willing to spend that extra money over there, right? So the general problem is that, when you go to a garage, you don't expect valet parking on a daily basis as a daily garage parking customer or a monthly parking garage customer. But you're still spending, at least, 10 to 15 minutes, and depending on the time you come into the garage, there could be like 6 cars queued up, and then so it's basically, it's not just the amount of time between, 10 to 20 minutes that are wasted. It's really when that time is happening, when people are like late for a flight or late for a meeting. And so it's not just about time, it's about timing. And so our idea is, to basically provide, affordable and autonomous valet parking services for garages to remove the pain and frustration from parking. And so a typical use case would be something like this, that you come to the entrance of the garage, and then you just get out of your car and you just activate, the autonomous valet parking from your car. And now your car does not have to be any fancy car. It just has to be a drive-by-wire car. And there are over 90 models and makes of drive-by-wire cars that are compatible with this service. So we do not have the traditional autonomous vehicle, problem of bootstrapping the market of, basically building out new vehicles. These are already existing vehicles. And basically with just a quick dongle to the CAN bus, these cars can now be connected to the app service from the car to the parking garage, and the parking garage will take over your vehicle and say, drive it to level 2, spot B14, which it has figured out is the empty spot for your car. So it is going to do the tracking, the planning, and the navigation of your car. But from your side, you're really just coming to the entrance of the garage and you say, okay, I'm done. You can hand over, and with peace of mind, you can walk away from the garage. And so here's a typical, like a plan of say a 2-story plan of a garage, where a car would come in, and then it would go, say, to a lower level, from level 1 to level 0 to find a spot over there. And so essentially the idea is that now once the car comes in at the entrance of the garage, we will automatically take this car, from the entrance, and it will be navigated through each of the stages of going through the garage, making turns and going, but the navigation will only be restricted from the entrance to the parking spot or any one of the available parking spots and back to the entrance. And the way we do this is by actually placing perception machines that have LiDARs, depth cameras, stereo cameras, and all at a pretty low cost right now. And where a garage could be retrofit for like under 100K for, say 3 levels. And now these basically can observe the vehicles as they come through. And these perception machines are basically placed at strategic locations that we can basically extract from the building, the CAD diagram of the building, and and be able to place them. And so essentially, this perception machine is observing the car from the entrance of this point to the exit. There is one facing the other direction, from looking at the car from the other direction. And then they together are doing collaborative perception, collaborative planning, and then collaborative control. These different perception machines are now connected to a gateway in the garage. And then the garages, in terms of the vehicles queuing, the state of the garage, the billing, all of that is managed in a cloud service. And so one cloud service could manage, say, about 40 garages. Each garage could be handling, up to 200 of these cars. The way this service would be introduced in the garages would be gradual. And essentially, these are sort of the different views of how the cars are being automatically teleoperated through the, So our end goal is not to necessarily just focus on, parking garages, in terms of, the need or the desperation. There is a slight need in COVID times. People, the garage occupancy has dropped a lot, and a lot of monthly customers have switched to being, daily customers. But the other need is really, in terms of, the a facility such as being able to now manage logistics services in a let me just pull up a different slide deck.
And Rahul, just so you know, you have about 1 minute remaining.
Sure. So where our research is focused on, I'll just not go to the slide. Where our research is focused on is that we're working with different industry partners in the logistics side for warehouse management, basically with forklifts, where a subset of the forklifts are now automatically teleoperated while working with manually operated forklifts within warehouses. And so essentially, the next generation of, Mobility 21, we want to extend, around, with logistics, with trucking, and where trucking do automatic docking and take over certain, distribution center functionality and between distribution centers, and also within the distribution centers and the warehouse. And we bring in basically end-to-end automation across the logistics pipeline. I'll stop over there.
Thank you so much, Rahul. And don't worry, you don't have to stop. We're just going to move into breakout rooms so that you can continue the conversation. So I'd like to thank everyone for their presentations.